We are just a few weeks into 2023 and already we've got another JWST milestone. It's discovered its first exoplanet. And not only that, an Earth-like exoplanet as well. You know me, usually I would save news stories like this for my monthly space news recap, my Night Sky News series, but this one, it was just too exciting and I just couldn't wait another week. So this was work done by Lustig, Jaeger and collaborators that was released after they presented it at the AAS meeting that happened last week in Seattle. It's the biggest astrophysics conference in the world with thousands of people there. If you want to get an idea of what it's actually like to go, my colleague Jim Davenport went and vlogged every single day of it, and I'll link his videos down below if you want to check them out. As you can imagine, off the biggest astrophysics conference in the world, there's been a flurry of new results coming in. It's just been a really exciting time to be in the field, to be honest, in the last few weeks. But this result especially caught my eye. So this new planet has been dubbed LHS 475b. That means it's the first planet to be discovered around the star LHS 475, also known as GJ 4102. It's about 41 light years away in the constellation of Octans in the far southern hemisphere. It's a red dwarf star, so it's a lot cooler and fainter than the sun, which unfortunately means you can't see it with your naked eye if you live in the southern hemisphere, and we're planning to go and try and find it tonight. Of course, it's no problem for JWST, and it managed to record a dip in the brightness of the star for about 40 minutes or so, which revealed that a planet was there and had passed in front of the star, blocking just a tiny little bit of its light. Now, the science team who applied for these observations did have some idea of when and where to look for this planet, and that's because of the TESS mission, the Transiting Exoplanet Survey Satellite, which monitors the brightness of around about 200,000 of the brightest stars near to the sun. It does so by splitting the sky into 26 patches or sectors and then staring at each patch for 27 days straight to monitor the brightness of the stars in that patch in the hope that we'll catch a dip in the brightness of a star in that time that hints at the existence of a planet. It's the follow-up to the Kepler mission, which people might be more familiar with, but it covers an area of sky 400 times larger. Now, once TESS detects a dip in the brightness of a star, it doesn't immediately get classed as an exoplanet, because there could be a lot of different explanations that could describe that dip from, something wrong with the analysis pipeline, or the fact that maybe there is a sunspot, a star spot on the star that's rotating into view, and that's what's causing the dip in brightness. Or maybe the star is just very variable and does dip in brightness and then increase in brightness every now and then. So it's not immediately flagged as an exoplanet. It becomes what's known as a TESS Object of Interest, or TOI. And they all go in this huge database that you can actually search. I'll put the link in the video description down below if you want to have a look yourself. But what it means is that science teams can then use that big database of TESS objects of interest to work out, okay, what do we want to follow up on? Now you can see here in the observing proposal for JWST that the science team put together, what they're specifically interested in is looking at planets orbiting dwarf stars. And that's because if you have a smaller star, it's likely that you're going to have smaller planets orbiting it, which means it's a great place to look for rocky terrestrial planets like Earth. And because dwarf stars are so much cooler, if those rocky planets were actually quite close into their star, they could still be in what's known as the habitable zone, where it's not too hot and not too cold for life. Them being closer into their star means that they pass in front of their star from our perspective here on Earth more often, meaning it's much more likely that we'll be able to detect a transit and then also confirm it when it comes back regularly as it orbits its star. That means if you want to find and confirm that there is an Earth-like planet that might be habitable somewhere out in the universe, then dwarf stars are a great place to start looking. As long as you have a telescope that is sensitive enough to detect the light from these dwarf stars, which, because they're so much cooler, are actually brighter in infrared light rather than visible light, which is where JWST comes in, and hence why this science team picked out TOI 901 from all of the TESS candidate planets to follow up on with JWST. And first they managed to confirm that yes, it is actually a planet. It wasn't a false positive, either an astrophysics false positive of a star spot rotating into view, or perhaps, some variability in the star, or a false positive from the actual data acquisition or even the analysis pipeline or whatever that might be. They confirmed that it was still there when they looked with JWST, and it was definitely a planet. Now, they did that by observing 2 transits of the planet, one on the 31st of August 2022 and one on the 4th of September 2022 using JWST NearSpec. That's one of the spectrographs on board at JWST. And what that means is that instead of it just taking an image of the object of whatever it's looking at, it also takes that light, splits it through a prism into its component wavelengths. So you can see, okay, how much of each wavelength of light are we receiving from this object? And that can tell you a lot about what the object is made of. They used it to record what's known as the light curve, where you record the brightness of the star over time, as well as taking a spectra at each of those instances as well. And they did that for 3 hours at a time to make sure they captured that 40-minute long transit, the shape of which proved it was definitely a planet and not a star spot rotating into view. You can also see in the black line there that they've fitted a model to each of these transits, basically a model of a planet orbiting a star. And by doing that, it gives you a couple of numbers. First of all, that the radius of the planet to the radius of the star is around about 0.03-ish, that the period of this planet is around about 2 Earth days, as in the time it takes to fully orbit its star. Its year is only 2 Earth days. And then the ratio of how far away the planet is from its star to the star's size is only 15.8-ish. To put that into perspective, the same number for the Earth and Sun system is 250. But with this ratio and already knowing how big the star is, you can work out, okay, well, how big is the planet? And you find out that it's around about 0.99 times the size of Earth. Now, to get at the planet's mass, you do need some different data. That's usually done by measuring how much a star wobbles, because the mass of the planet offsets the center of mass that the two orbit around from the very center of the star, so it appears to wobble around on the sky. That's a lot easier when you have a much bigger planet around a smaller star, because the effect on the star's motion is going to be a lot more. But we have managed to do it with some smaller, rockier planets around dwarf stars before. So because the authors of this study didn't actually have that data, what they did was assume this planet had a similar density to the rocky planets that have been found around dwarf stars in the past, and so used that to estimate that its mass should be around about 0.9 times the mass of Earth. So it is very Earth-like, this exoplanet, but also at the same time drastically different as well. Taking just 2 Earth days to fully orbit the star. It's very, very likely that this planet is tidally locked to the star. So what that means is that it always shows the same face to the star, and one side of the planet always faces away from the star instead. Essentially, like its day, the time it takes to spin on its axis, is the same as its year, the time it takes for it to fully make one orbit of the star. That's exactly what we see with our own moon as well, right? We only ever see one side of the moon, and the far side is always pointing away from us. So if one side is always facing its star, that's going to be a lot hotter than the other side. And the question is, what does that do to a rocky planet's atmosphere? Now, the goal with this science project has always been to try and characterize the atmospheres of these planets. Because the question has always been, can rocky planets orbiting that close into dwarf stars actually retain their atmospheres, or will it just completely boil off? Now, the eagle-eyed among you will have noticed that they also intend to target TRAPPIST-1H in this project, which as a system, TRAPPIST-1 has a lot of hype around it over the question of whether these rocky planets are habitable. So to try and characterize the atmosphere of LHS 475b, what they did with NearSpec on JWST was record what the spectrum of light looked like before the transit, where you split the light into its component wavelengths, and then they did the same thing during the transit and subtracted one from the other to get the impact of the planet's atmosphere as the light passed through it. Those gaps where you see certain wavelengths are missing is because of molecules in the atmosphere of a planet stealing away very unique wavelengths of light that reveals that those molecules are there, kind of like a fingerprint. Now, we know it's possible to do this with JWST. It's been demonstrated a couple of times now, not least back just in December 2022 with the planet WSP-39b, which is what's known as a hot Jupiter, a Jupiter-sized planet that's very close in to its star. I talked about it on this channel when the news was released. I'll link that video down in the video description if you want to check that out. But in this spectrum, what's known as the transmission spectrum, you can see all of those clear signatures that reveal that carbon dioxide is present in this planet's atmosphere, water, sulfur dioxide are all there as well. The signal is very strong because it's a very big planet with a thick atmosphere. Compare that then to the spectrum for the much smaller and fainter LHS 475b. The white dots there are the actual data that was recorded by JWST, and you can see it's much noisier than what we just saw for WSP-39b. It's nowhere near as clear-cut what's going on here. Now, the coloured lines are different models for what the atmosphere could contain. Yellow being absolutely no atmosphere whatsoever, blue being a pure carbon dioxide atmosphere, and green a pure methane atmosphere, CH4. Now, the only one that the authors claim we can rule out with any certainty because it doesn't really fit the data is that pure methane model for the atmosphere in that green line there. But for the other two models, it's harder to tell. It kind of could be both. Now, the spectrum I just showed was the one that was released by NASA in the press release. It was probably what you saw all over social media and in the news outlets. But in the actual research paper where the authors of this study actually wrote up the work, when they showed the spectrum, they actually showed a lot more models to compare the data to, and also gave what's known as the chi-squared value for each model. Chi-squared is essentially a statistical test that lets you say how good of a fit is this model to this data. And essentially, the closer the number is to 0, the better fit the model is. So here's the version they showed in the actual paper. In the top panel here, you can see different hydrogen atmospheres, and you can see they don't fit the data at all. The chi-squared values are massive. Then in the bottom panel, you've again got this pure methane atmosphere that we saw in the previous version in pale lilac now, that has a much higher chi-squared value than the rest of the models, so it's ruled out by the statistics. But they've also plotted a pure water atmosphere and an Earth-like atmosphere as well. Now you can see those are slightly less likely than the pure carbon dioxide atmosphere that we saw before, but the model with the lowest chi-squared value that comes the closest to 0 is the one where you have no atmosphere around this planet. Meaning that with this data that we have, the most likely explanation for it is that this planet does not have any atmosphere and that it's been probably entirely boiled off by the star. Although, there could be another explanation, and that could be that the planet actually has a very thick atmosphere, but with lots of clouds, very similar to Venus or Titan in the solar system. If you had thick clouds like that, they wouldn't allow a lot of the light from the star to pass through the actual atmosphere itself, so you wouldn't get any of that absorption taking place to tell you what was present in the atmosphere. And with just the transit data, it would almost be impossible to tell whether there was no atmosphere or whether there was very thick clouds. So it's difficult to say at the minute whether this planet has a very thin carbon dioxide atmosphere like Mars, or a thick cloud-heavy atmosphere like Venus, or perhaps even no atmosphere at all like Mercury. Thankfully, there is another observation of a transit of LHS 475b that's scheduled for summer 2023. And that's exciting because with 3 transits, you'll be able to stack even more data together and hopefully get a much stronger signal if there is any absorption happening through the atmosphere. Ideally, you'd also like to look at the transit with MIRI, JWST's far infrared detector, because MIRI would be able to tell the difference between a planet with no atmosphere and a planet with thick clouds. Because a planet with thick clouds would be much hotter than a planet with no atmosphere at all, and the far infrared lets you probe the temperature. The science team didn't ask for those observations though in their original proposal, so they will have to write another one in the next round of observations, the deadline for which is fast approaching on the 27th of January 2023, so they best get a wiggle on. But for now, we might have found our first hot Earth, like the hot Jupiters of the exoplanet world, you know, that's very similar to Earth, but's had a very different evolutionary history. I think it just goes to show how much of a game changer JWST is going to be in the exoplanet field. You know, we've been so biased for so long to big planets that orbit very close into their stars that with JWST we could finally start to populate sort of the empty parts of this diagram of radius of planet versus orbital distance if TESS and JWST continue to work together to find candidates and then follow up on them in this way. And you know what? I think the authors of this study on LHS 475b, Lustig, Jaeger and collaborators, really sum this up best, just in the last line of the research paper that they wrote, where it says, our findings only skim the surface of what is possible with JWST. Before we get to the bloopers, I just want to say a big thank you to Brilliant for sponsoring this video. If you've been following me for a while now, you'll have heard me talk about Brilliant on my channel before, and it's just because I think it really is the best way for you to learn a new concept in science and maths right now. For those who don't know, Brilliant is a website and an app with a huge range of interactive courses across science, maths, and computer science. And it's that interactivity that makes Brilliant stand out. It really does allow you to properly get to grips with the topic, you know, learn by doing and build up your physical intuition and confidence for what's going on. After watching this video, you might want to learn more about how we detect exoplanets and start plugging in some numbers yourself with their astrophysics course. I briefly touched on the wobble method in this video, but if you want to know more, check out the course that Brilliant has on it. It really is fantastic as an introduction. So you can head to brilliant.org/Dr. Becky and you can sign up completely for free. Plus that link is also in the video description down below, and if you go to it, you'll get 20% off an annual premium subscription. At that link, you'll also find my personally curated learning path for you with the courses that cover the topics that we chat about the most in my videos. So thank you so much to Brilliant for sponsoring this video. And now, roll those bloopers. God, so ungraceful. Get on the chair, Becky, get on the chair. Now, the science team did have some idea over when and where to look for a planet around a red dwarf star, thanks to the TESS mission, the transiting exoplanet no, that's only one S. What does the other S stand for? Space satellite? No. That sounds naff. They wouldn't call it that, would they? What does the second S stand for in TESS? TESS mission survey. Should have guessed that. And they also give what's known as the chi-squared number, which is essentially a statistical test. Do it very easily, and therefore you wouldn't get a very strong signal with your transmission. You're nothing gonna break my stride. Nobody gonna slow me down. Oh no, I got to detect that transit.